Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry Paper 3. In the Unit 5, we are studying about reactions of synthetic importance. Lecture 3, we are studying about Beckmann rearrangement, Schmidt and Claisen Schmidt reaction. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered include Beckmann rearrangement. Here we will be studying about nomenclature, stereochemistry, mechanism and applications of Beckmann rearrangement. Afterwards, we will be studying about Schmidt reactions. Here we will be studying about the mechanism and applications of Schmidt reaction. Then we will also be studying about the comparison between Beckmann rearrangement and the Schmidt reaction. Then finally we will be studying about Claisen Schmidt reaction. Here we will be focusing mainly on the mechanism and application. Welcome to the next session. In this session we will be studying about Beckmann rearrangement in the beginning. So what is Beckmann rearrangement? Beckmann rearrangement is the conversion of ketoximes to substituted amide. Actually this reaction happens in the presence of acidic reagents or Lewis acids. So here is an example which is shown here. This is the ketoxime. So this is formed from the ketone and hydroxylamine. So that is what is called the ketoxime. And this ketoximes in the presence of an acid undergoes Beckmann rearrangement to give the corresponding amide derivative. This is a substituted amide derivative. And this was discovered by Beckmann in the year 1886, and it was actually called a skeletal rearrangement. Skeletal rearrangement means the skeleton of the molecule, that is how the groups are actually arranged. The overall skeleton is changing, because if you look at here, this is a carbon, this is a carbon, this is a nitrogen, this is an oxygen. So the link we can say here is carbon, carbon, nitrogen, oxygen. So that link is now changed to carbon, nitrogen, carbon and oxygen. So this is the overall skeletal of the molecule changes. So this is what is called skeletal rearrangement. And when we take the case of aldoximes, aldoximes are less reactive compared to ketoximes. And when the aldoximes undergo Beckmann rearrangement, we end up with a nitrile. So in the case of ketoximes, we get a substituted amide derivative, whereas in the case of aldoximes, we get a nitrile or a cyano compound. So let us look at some of the characteristics of this particular rearrangement. So the Beckmann rearrangement is occurring in both the cyclic and acyclic compounds. And the cyclic oximes yield lactams and acyclic oximes yield amides, substituted amides. So this is the one we have seen earlier. And the major use of Beckmann rearrangement is in the study of finding the structure of the ketone. In earlier days, people were not having many spectroscopic technique to find out the structure of the compound. In those days, people used Beckmann rearrangements to find out the structure. So if it is a ketone, the structure of the ketone can be identified using Beckmann rearrangement. So here what happens is the ketone is converted to the oxime and it is subjected to Beckmann rearrangement, and we end up with the amide, rearranged amide derivative. So that rearranged amide derivative is hydrolyzed, and amide on hydrolysis gives an acid and an amine. So based on what is the acid obtained and what is the amine obtained, because acid is acidic in nature, amine is basic in nature, so it is very easy to identify which amine and which acid it is. From that we can actually backtrack and identify what was the starting ketone. So this was one of the earlier methods when people use Beckmann rearrangement for identifying the structure of the ketones. And let us look at what are the different reagents which are used in this reaction. Basically, Beckmann rearrangement is initiated by acidic reagents. So the different acidic reagents that are used include concentrated sulfuric acid, hydrochloric acid, PCl3, thionyl chloride, zinc oxide, polyphosphoric acid, etc. And the Beckmann mixture, the original Beckmann rearrangement was carried out using HCl in acetic acid, acetic anhydride mixture. And some of the Lewis acids that were used in this reaction include PCl5 and silica. So before we move forward, let us look at how we give the nomenclature for these oximes. So in the case of aldoximes, the relationship between the hydrogen atom and the hydroxyl group in the oxime is considered for syn and anti. Basically, the oximes can be syn oxime or anti-oxime. So here in the case of aldoximes, whether the hydrogen and the hydroxyl unit, whether they are on the same side with respect to the carbon-nitrogen double bond, or they are on the opposite side with respect to the carbon-nitrogen double bond, is considered for naming it. So if the hydrogen and the OH are on the same side, it is called the syn aldoxime, and if the hydrogen and the OH are on the opposite side, it is called anti-aldoxime. Because in aldehyde we only have one alkyl group and a hydrogen, and since the name given is ald is for the hydrogen unit, aldehyde's hydrogen unit, so we use hydrogen as the reference for naming aldoximes. And if you look at ketoximes, we have two possibilities, because in this particular case, let us look at methyl group is there, ethyl group is there. So this compound can be named after the methyl ketoxime or a ethyl ketoxime. So that way we can actually give the name in different ways. So based on how we are giving the compound's name, because this is given as methyl ethyl ketoxime. So that means the methyl group, whatever is given in the beginning, that is the first group, and the hydroxyl unit, whether they are on the same side or they are on the opposite side, we give syn and anti nomenclature. So this compound is now named after the methyl group and the hydroxyl OH group are on the same side, so between the carbon nitrogen double bond. So this is called syn methyl ethyl ketoxime. And in this particular case, the methyl group and the OH are on the opposite side of the C double bond N. So this is named as anti-methyl ethyl ketoxime. So we have to have some reference alkyl group. Based on that reference alkyl group, where the hydroxyl is present, the ketoximes are named. In olden days, people generally use alpha for syn and beta for anti. If you are looking at very old literature, so the syn aldoxime is written as alpha aldoxime, and the anti aldoxime or the ketoxime is written as beta. So this is how earlier people used to name these compounds. Now let us look at the stereochemistry of this reaction. For unsymmetrical oximes, there are two possibilities exist. That is, as we know, there is a migration. When we look at the mechanism, we will be understanding what we are actually discussing here. So in the case of the skeletal rearrangement, we said the one of the alkyl group migrates from the carbon to the nitrogen. So that is what is basically the Beckmann rearrangement. So which group actually migrates, which is anti to the hydroxyl group, that is what it decides. So in this particular case, what actually happens is, in most cases, the group that is anti to the OH group migrates from carbon to nitrogen. So this is what is the overall stereochemistry of the reaction. So this is how, when we look at the mechanism, we will understand this. Say for example, here in this particular case, the methyl group is anti to the hydroxyl unit. The OH and methyl are in the opposite side. So when the Beckmann rearrangement happens, this methyl group migrates from this carbon to nitrogen. So as you see here, this nitrogen is not having the hydroxyl. Instead of that, the nitrogen is having a methyl group. So that means the migration of this alkyl group happens from the carbon to the nitrogen. So we end up with a benzamide derivative. So this is the aromatic unit ARCONHR prime. So this is what is the benzamide derivative. So nothing but if you break the molecule here, we end up with a benzoic acid. So this is the benzamide derivative. And if you look at the other one, in this particular case, the aryl group is anti to the hydroxyl group. So when this compound is subjected to Beckmann rearrangement, this aryl group now migrates from the carbon to the nitrogen. So we end up with the MECONHAR. In other words, this is the aniline. ARNH2 is nothing but the aniline, and this is the aniline derivative. So this is nothing but the acetanilide derivative. So benzamide and acetanilide are the two different products that are formed by the anti-migration, and for this particular migration, the group which is anti to the hydroxyl is the one which migrates. Now let us look at the mechanism of the Beckmann rearrangement. So as we mentioned earlier, we have two major conditions. One is a strong acidic conditions, and another condition we also have a acid chloride. So when strong acidic conditions are present, that means sulfuric acid, HCl, like strong acids are present, they follow one type of path. And when acid chlorides are present, the same reaction follows a different path. Acid chloride we can also use thionyl chloride, or even normal acid chlorides can be used. So what is the difference between these two reagents taking place two different pathways is basically when we have a H plus ion, that is the acidic, strongly acidic condition, this hydroxyl is actually protonated, and this is the first step that happens. In that case, the strong acid O protonation followed by loss of water molecule gives the carbocation after the migration of the R group, because one of the R groups migrates from the carbon to the nitrogen, so that leads to the carbocation. So here the loss of water molecule happens, but in the case of acid chlorides, this OH is a very good leaving group. It leaves as a OX minus. So there is no water molecule loss when we use acid chloride, because this is a ester unit, and this ester is a very good leaving group. Again, the migration of R group is common in both the cases, but which group is lost is the only thing that is different between the acidic conditions and the acid chloride conditions. So from the after the formation of this carbocation, this is treated with water to give this particular intermediate, and this intermediate loses a proton to give the enol, and this enol finally tautomerizes, because this enol is quite unstable. So this undergoes tautomerization to give the final amide derivative. So this is how the overall Beckmann rearrangement takes place. And from the crossover experiments, there was no crossover product formed in this particular reaction. So that shows us the migration of the alkyl group to the nitrogen is a intramolecular one. If there is if this R group detaches itself and then it reattaches itself to the nitrogen, during that process we can have crossover products. But in this Beckmann rearrangement, it was confirmed that there is no crossover products. So in other words, we can say the migration of the R group happens intramolecularly. And when we look at the migratory aptitude, that means which group will migrate very quickly. Hydrogen migration is far more easier compared to phenyl migration, followed by tertiary, secondary and primary alkyl groups. So here is an example. We have a primary alkyl group, that is the methyl group is present here. We have a aryl group which is present here. So when we treat this with the hydroxylamine to form the oximes, we end up with the two types of ketoximes. One is the anti-isomer with respect to the aromatic ring. So this aromatic ring and the OH are in the anti-orientation. So this undergoes Beckmann rearrangement in the presence of sulfuric acid at a much faster rate to give the corresponding anilide derivative. Whereas when we take the syn isomer, the methyl group or the primary alkyl is anti to the hydroxyl unit. So in this particular case, the migration happens very slow. So that is the reason the benzamide derivative is not formed very quickly. So this way we can actually confirm the migratory aptitude of the substituent that is present on the carbon. So let us reiterate what we have seen so far. For the migratory aptitude, hydrogen migrates much faster compared to the phenyl group, followed by tertiary, secondary and primary alkyl groups. Let us look at some of the examples of Beckmann rearrangement in the drug synthesis. The first one we will look at paracetamol synthesis. Paracetamol is synthesized from phenol. So yeah, this is a industrially important process. So in this method, what happens is the first step is the acetylation of the phenol, which gives the para substituted acetyl derivative. So this is treated with hydroxylamine to form the corresponding oxime derivative, and this oxime derivative in the presence of trifluoroacetic acid leads to the paracetamol after Beckmann rearrangement. So this is the acid catalyzed Beckmann rearrangement for the preparation of paracetamol starting from phenol. The next one is the synthesis of azithromycin. So the azithromycin can be synthesized from erythromycin oxime. So this is the erythromycin oxime part. So this erythromycin oxime part undergoes Beckmann rearrangement in the presence of acid, and after further reactions with the reduction and Eschweiler-Clark methylation, finally azithromycin is formed. But the crucial reaction is nothing but the Beckmann rearrangement of the erythromycin oxime. So this erythromycin oxime undergoes rearrangement. So here what happens is the ring enlargement takes place in this particular case. So for the convenience, these substituents are marked as R and R prime group in the products. Another important industrial process is the preparation of nylon 6. So the nylon 6 is prepared from the caprolactam monomer. So how the caprolactam is synthesized is basically based on once again the oxime rearrangement, that is the Beckmann rearrangement. So either phenol, the starting material can be phenol or cyclohexane. So there are two different industrial process, both leads to the same intermediate, that is the cyclohexanone is the starting material for this entire process. So phenol can be converted to cyclohexanol and followed by oxidation leads to the cyclohexanone, or cyclohexane can be oxidized to give the cyclohexanone. So this cyclohexanone is treated with hydroxylamine. This gives the cyclohexanone oxime. So this is a crucial material which is the starting material for the Beckmann rearrangement. And this cyclohexanone oxime is treated with sulfuric acid and sulfur trioxide leads to caprolactam in a industrial scale. So this is another major application of Beckmann rearrangement. Let us look at Schmidt reaction. So the Schmidt reaction is nothing but the acid catalyzed reaction of hydrogen acid, that is hydrozoic acid, with electrophiles, basically carbonyl compounds, tertiary alcohols or alkenes, leading to the formation of amines, nitriles, amides or imines after the rearrangement and expulsion or extrusion of nitrogen. So acid, when treated with the hydrozoic acid in the presence of sulfuric acid, gives amines with the loss of CO2 and nitrogen gas. Aldehydes undergo the same reaction to give nitriles. Here water and nitrogen are the byproducts, And when we take ketone as a starting material, the Schmidt reaction produces an amide derivative with the loss of nitrogen gas. So three different starting materials undergo the same reaction with the reagent, producing three different end products. Let us look at the reaction mechanism for this reaction. So if we start with the acid and treat with the hydrozoic acid, the intermediate formed in the reaction is a isocyanate, and this isocyanate give amine. So let us look at each individual step how the reaction actually proceeds. So the reaction is actually carried out in the presence of strong acid. So the initial step is the acid, the hydroxy group of the acid is protonated. So this is the first step, and this loses a water molecule because this is a very good leaving group, and the loss of this water molecule leads to the carbocation. So this carbocation is now attacked by the hydrozoic acid, and this leads to this particular intermediate, and this intermediate actually undergoes the alkyl migration. So this R group is now migrating from the carbon to the nitrogen. So this is a crucial step, and after the migration of the alkyl group, nitrogen is lost. So this migration is very similar to the Beckmann rearrangement. This migration in this Schmidt reaction is also a concerted migration, that is intramolecular migration. So this leads to the isocyanate formation happens, and this isocyanate is being attacked by the water molecule, and it leads to the intermediate which is unstable, and this loses carbon dioxide molecule to give the amine as the final derivative. So in other words, an acid can be converted to the amine. So if you look at here, the alkyl group remains the same. There is loss of one carbon atom. So if you look at the conversion of acid to an amine, in this particular case, there is a loss of one carbon atom in the form of carbon dioxide. So this Schmidt reaction gives acid to amine with loss of one carbon atom. And there is a different mechanism for ketones. So in the previous one we saw about the acid, how the acid can be converted to the amine. When we start with the ketone, we end up with the final product as an amide. So here the reaction mechanism is little bit different. So in the case of ketone, the initial step is the protonation of the carbonyl oxygen. So this carbonyl oxygen, once it is protonated, the oxygen is electronegative. So this pulls the double bond electron towards itself. So this carbon becomes more electrophilic, and this electrophilic carbon is being attacked by the acid anion. So that leads to this particular intermediate, and this is where there are two pathways by which the product can be formed. One pathway follows very similar to the Baeyer-Villiger reaction. Another pathway follows through the Beckmann rearrangement pathway. So in other words, what is the major difference between these two pathways is nothing but, in one case, because the intermediate, this intermediate, a proton is added. So whether it adds to the nitrogen or it adds to the oxygen. So based on where the proton is added, the reaction takes different pathways. If the proton is added to the hydroxyl unit, that is, it leads to the water for H2O plus formation. So this follows a Beckmann rearrangement pathway. If the proton is added to the nitrogen, then it follows the Baeyer-Villiger pathway. So this is the major difference between the two pathways for the product formation. So let us follow the Baeyer-Villiger pathway first. So now the proton adds to the proton is being abstracted by the nitrogen, and followed by the immediate rearrangement, that is the alkyl group from the carbon now migrates from the carbon to the nitrogen, and the nitrogen gas is lost simultaneously. So two things happen simultaneously. the migration of the alkyl group followed by the loss of nitrogen gas. That leads to this particular carbocation intermediate, and this carbocation intermediate is quite unstable. So the nitrogen is having a lone pair, so it donates the lone pair between the carbon and the nitrogen, so that leads to the formation of a double bond here. And in the initial step, the acid is formed, so that acid abstracts a proton from the OH group. That leads to the final formation of the amide derivative, because rearrangement of electrons takes place, which leads to the final amide rearranged amide derivative formation. So this is how the Baeyer-Williger pathway happens. And if you look at the Beckmann pathway, instead of the nitrogen, this OH actually abstracts the proton. So this forms the H2O plus, and H2O plus is a very good leaving group. So this intermediate loses water molecule, and in this particular step, this alkyl group migrates to the nitrogen, and the nitrogen is lost simultaneously. So that is how we had written nitrogen loss. So these two happen simultaneously. Like in this particular case, this is what is the Beckmann pathway, because the alkyl group migrated from this carbon with its bonded pair of electrons. The carbon becomes electron deficient. In other words, we have a carbocation. So that is what is formed here, and the nitrogen donates its lone pair between the carbon and nitrogen. So we end up with a nitrile like a derivative where nitrogen is having a positive charge. So this is being attacked by the water molecule that is present in the system, and we end up with this particular corresponding intermediate, and this intermediate loses water molecule, and finally we end up with the this is the enol derivative, which we have seen in the Beckmann rearrangement also. So this enol is quite unstable, so this tautomerizes to give the corresponding substituted amide derivative. So this is the two pathways by which a ketone can be converted to amide. So the crucial step is where the proton is added, whether it is added to the nitrogen or to the hydroxyl, decides which pathway the reaction actually follows. Now when we look at the stereochemistry of this reaction, the stereochemistry here is actually retained. So if we start with the S plus isomer and 2-phenyl propanoic acid. So we are starting with the S isomer. We end up with the final product as the S isomer. The carboxylic acid is lost, and we end up with the amino derivative. So in this particular case, we have only carbon, carbon and hydrogen. So here also we have carbon, carbon and hydrogen. So the priority did not change. Only the carboxylic acid unit is lost, and we end up with the NH2 derivative. So this clearly shows that Schmidt reaction actually gives the retention of product. And if we take the biphenyl derivatives as shown here, this carboxylic acid is converted to the amino derivative, and here again what we are ending up is the retention of configuration. So in other words, the stereochemistry of Schmidt reaction is a retention of configuration. And let us look at some of the applications of Schmidt reaction. So the Schmidt reaction has been used for the synthesis of quinine. So this particular starting material is converted to the corresponding lactams using sodium acid in polyphosphoric acid, and this after various steps is converted to quinine derivative. So this is a crucial Schmidt reaction which is essential for the heterocyclic ring formation. And in the case of triquinoxine derivative formation, here again this particular carboxylic acids are converted to the carbonyl derivative, and this on further various transformations leads to triquinoxine derivative. So this is another example of Schmidt reaction. And if we look at which group will migrate, because we already had seen there are possibility of a different alkyl group migration. So in this particular case, we have a aromatic ring having a fluorine derivative, and there is another aryl derivative. So when this particular compound is subjected to Schmidt reaction, so this is the ketone. So in this particular case, we have the aryl derivative with the fluorine, and we have a imidazole derivative as shown here. So these two groups can undergo rearrangement. So either the aromatic ring with the fluorine can undergo rearrangement, that is the shift can happen from carbon to nitrogen, or this particular imidazole derivative can move. So when we conduct the reaction with sodium acid in sulfuric acid, the Schmidt reaction, this product is formed only in 27 percentage. That means the aryl migration, because if you look at here, the group attached to the ketone carbon, fluoroaryl derivative migration, which leads to this particular product, whereas when the imidazole unit is migrated, we end up with a 70% of the product. So in other words, what we can say is between imidazole and the aryl derivative, imidazole derivative is a better migrating group compared to the aryl derivative. So here, as we mentioned, this reaction favors the imidazole migration over the aryl migration. And there is also another reaction as shown here. In the first step, the Diels-Alder reaction between these two substrates leads to the cyclic derivative here with the acid unit, and we have the carbonyl. So this is a intramolecular Schmidt reaction. So in this particular case, we end up with the cyclic derivative as shown here. Then finally, if we take this particular case, change of solvent, especially the acidic conditions, leads to two different type of product. When we take this particular ketone and do the Schmidt reaction with the concentrated HCl, we end up with this particular product, whereas when we use sulfuric acid, the migration takes place in a different way, leading to the isomeric product of this one. So in other words, what we can say, by changing the corresponding acids which are used in the Schmidt reaction, we can actually carry out or obtain different type of products. We have seen that the compound A, as shown here, undergoes Schmidt reaction to give two different products. One is C and another one is D. So why these two products are formed, and what is the reaction mechanism by which this is formed, we will be now looking at. So as it was mentioned earlier, if we are using sulfuric acid, then this Schmidt reaction actually produces the compound D, where aryl migration takes place. Why this happens? Simply because the intermediate in the first step, what happens is, this is the intermediate that is formed, that is the acid attacks this electrophilic carbon, and this intermediate is formed, and this intermediate actually loses nitrogen to produce either C or D. Under the reaction conditions, when we are using sulfuric acid, this is considered as anhydrous conditions, and this intermediate loses water in the initial step to lead to this kind of intermediate, and this undergoes the aryl migration by the concomitant loss of nitrogen also to give this rearranged compound. So in the presence of sulfuric acid, which is a dehydrating agent, this kind of rearrangement takes place. And now the loss of water can also produce a syn isomer, because we have anti-isomer and the syn isomer. The anti-isomer is the one which is formed because in the case of syn isomer, there is peri-interactions from the hydrogen that is present here. So this hydrogen and these two nitrogens are in close proximity, and due to steric repulsion, this syn isomer is not formed. In other words, the loss of water molecule only leads to the formation of the anti-isomer, and this anti-isomer undergoes the aryl migration. From this part is migrated to this nitrogen to give the final product D, and this happens because sulfuric acid is a anhydrous solvent. So this removes water very efficiently, and this is the mechanism by which we are getting the aryl migration. Now let us look at the HCl case. In the case of HCl also, the intermediate formed is a similar one, but the HCl reaction is an aqueous conditioned reaction. So that means there are plenty of water already present in the reaction medium. So the loss of water molecule cannot happen in the first place, due to which the loss of nitrogen atom only takes place, which leads to the formation of, after the alkyl migration, that is, this bond migrates to give a benzyl carbocation. And if the aryl migration takes place, then we are going to get a alkyl cation. So there are two ways the reaction can follow. One is the alkyl migration pathway, which leads to the benzyl cation, and the other one is aryl migration, which leads to the alkyl cation. So we already know the stability between benzyl cation and the alkyl cation. Benzyl cation is more stable. So this is the exact mechanism by which the rearrangement takes place in the case of HCl. That is, even though we are using concentrated HCl, the concentrated HCl is still an aqueous solution only. So like the sulfuric acid case, the initial step is not the loss of water molecule, but loss of nitrogen is the initiation for this migration under HCl acidic conditions. So this is the reason both sulfuric acid and HCl gives different types of aryl and alkyl migrated products in this particular Schmidt reaction. So let us do a small comparison between the Beckmann rearrangement and the Schmidt reactions, because in the Schmidt reaction we are starting from a cyclic ketone, and in the case of Beckmann rearrangement we are starting from a ketoxane. In other words, the one more additional step is required for the Beckmann rearrangement to happen. So we can use either ketones or ketoxanes as the starting material, depending on what is the rearrangement we are focusing on. And the alkyl aryl migration ratio of the individual reactions varies depending on the reaction conditions. As we had seen for the Schmidt reaction, sulfuric acid and the hydrochloric acid conditions give different types of products. So this is possible by changing the reaction conditions. So this is applicable for Schmidt reaction. And in the case of, as we have seen, we can also use concentrated hydrochloric acid or concentrated sulfuric acid. So both leads to different types of products. And in the case of Beckmann rearrangement, we are using acid catalysts such as sulfuric acid, polyphosphoric acid, phosphorus pentachloride, thionyl chloride, etc. can be used in the case of Beckmann rearrangement. So this is the comparison, in other words, the similarity between these two reactions. And the Schmidt reaction is actually one step lesser compared to Beckmann rearrangement, because here the cyclic ketone is directly used, whereas in the case of Beckmann rearrangement we have to convert the cyclic ketone into the corresponding ketoxane. But again, there are major differences exist between these two reactions, because even though one extra step is done, many times Beckmann rearrangement is a very clean reaction, giving a higher yield of the product, whereas the Schmidt reaction gives poor yield. So even though the number of steps are more, the final product formation actually decides whether we will choose the Beckmann rearrangement or the Schmidt reaction. Now here is a comparison between the different reaction conditions, that is the Schmidt reaction and the Beckmann reaction. For the starting material A, the cyclic ketone is the starting material. So when we use the cyclic starting material, the ketone, we run the reaction, that is the Schmidt reaction. So we have HCl condition or we have sulfuric acid conditions. And if you look at the major product, in the case of HCl, we only have 52% of the product, whereas in the case of sulfuric acid, we are getting the 75% of the major. That is, the C isomer is formed exclusively in the HCl condition with the 52% yield, whereas the D isomer is formed in 88% with isolated major yield of 75%. So this is the difference in the case of Schmidt reaction, whereas when we use Beckmann rearrangement, the use of phosphoric acid, especially polyphosphoric acid, gives D as an exclusive product with the 60% yield. So when we compare between Schmidt reaction and the Beckmann rearrangement, the Schmidt reaction gives mixture, whereas the Beckmann rearrangement, even though the yield is little bit less for the product D, it is the only or the exclusive product in this particular case. And when we use the thionyl chloride for the Beckmann rearrangement, the C is formed in 92% yield, but the isolated yield of the major product is only 48%. So in this particular case, Schmidt reaction is better for preparing this particular intermediate, that is C, whereas for the product formation D, we may use Beckmann rearrangement. So that is the reason, even though we have two different conditions, the starting materials are also different, but the product formation and the ratio of the isomers are the crucial things which decides which type of reaction we can actually follow. And when we look at practical considerations, sometimes the Schmidt reaction is favored over Beckmann rearrangement because one step less. That depends on how much of the yield we are actually getting. So sometimes Schmidt reaction is favored because one step is less. But when the Schmidt reaction does not give the desired lag term, or when the yield of the reaction is low, people prefer the Beckmann rearrangement. So that is the reason it is the end product basically that decides what is the optimal condition for that particular reaction. And when we have to use between for polyphosphoric acid and thionyl chloride, people prefer polyphosphoric acid because the use of polyphosphoric acid always gives a very cleaner reaction product. So these are some of the practical considerations we have to look into, and we cannot simply always go by what is the maximum yield or which is the isomer that is formed. Depending on our requirement, we have to choose the reaction condition for that particular reaction. Then let us look at Claisen Schmidt condensation reaction. So what is the Claisen Schmidt condensation reaction? This reaction is a reaction between an aldehyde or ketone having an alpha hydrogen with aromatic carbonyl compound lacking an alpha hydrogen. So that means we have one carbonyl unit, another carbonyl unit. One of the carbonyl unit can be ketone or aldehyde. Here we have a alpha hydrogen, and another carbonyl unit here we don't have a alpha hydrogen. So the presence of alpha hydrogen on one carbonyl compound and absence of alpha hydrogen on another carbonyl compound. So this is crucial for the Claisen Schmidt condensation. When these two compounds are reacted together in the presence of a strong base, we end up with a Claisen Schmidt product, or in other words we call this as a cross aldol condensation product. So in the case where the product formed is still reactive alpha hydrogen, if it is present and the hydroxide adjacent to the aromatic ring, then the reaction will quickly undergo dehydration to the leading to the dehydration product. So here, instead of the aldol derivative, we are actually having a alpha beta unsaturated compound. So that means there is a hydroxyl unit which underwent dehydration to give this particular alpha beta unsaturated system. So when we look at the mechanism, we will see how the reaction actually proceeds. And this reaction is applied for the preparation of chalcones, flavone, and many natural products. So let us look at the mechanism in detail. So the initial step is, because this is a base catalyzed reaction, so we have a acidic proton, that is the alpha hydrogen which is present to the carbonyl group. So this is the most acidic proton. So this proton is being abstracted by the base, strong base. So that leads to the formation of a carbanion. So this carbanion can be resonance stabilized with the negative charge residing on carbon, or it can also reside on the oxygen as shown here. So this is the enolate derivative. So once this is formed, this carbanion now can attack the aromatic aldehyde, that is the compound, without having the alpha hydrogen. So this is the one which is being attacked by the carbanion. So this leads to the intermediate as shown here, and this is the hydroxy derivative which we were talking about. Whenever there is an aromatic system, as we mentioned earlier, so if there is an aromatic system present in this system, then it facilitates the loss of water molecule. So the base which is present in the medium abstracts a proton, that leads to the concomitant loss of the OH group. So water is lost, which leads to the formation of the chalcone-like derivative, that is the alpha beta unsaturated systems are present. If there is no aromatic system, then the reaction may end up or stop here. So this is nothing but the cross aldol product. So what is the driving force for the elimination of water is nothing but the extension of conjugation. So once this water is lost, we have an aromatic ring which is having 3 pi bonds, and there is another pi bond, there is another pi bond. So there is an extension of conjugation possible in this system. So this is the driving force for the dehydration. Now this Claisen Schmidt condensation has been used in various synthetic processes. So the first one is the dibenzyl acetone formation. As we mentioned earlier, if the starting material, that is the carbonyl compound, has more than one alpha hydrogen, so the reaction can happen multiple times. So in this particular case, 2 molecules of benzaldehyde reacts with acetone. So in this particular case, this is the central acetone unit which is present here. So one side and the other side. So in both the sides, like we have an alpha hydrogen here, we have an alpha hydrogen here. So in both the sides, the Claisen Schmidt condensation takes place to give the dibenzyl acetone as shown here. So the Claisen Schmidt condensation can also be used for the synthesis of chalcone derivatives. So here, as one of the example is shown here. In this particular case, substituted benzaldehyde is reacted with substituted acetophenone. These two react together in the presence of a base, giving this particular chalcone derivative. So Claisen Schmidt condensation can also be used in the synthesis of Engelhardione. So this total synthesis is given here. Of course, the reaction involves various steps, and one of the crucial steps for the formation is through the Claisen Schmidt condensation reaction. This ketone derivative is reacted with the substituted benzaldehyde derivative. These two form the condensation, and that is how the main ring is actually synthesized. So from that, basically the last synthesis of the ring cyclization happens through some other condensation reactions, but the overall structure of this particular derivative is synthesized using Claisen Schmidt condensation reaction. In the synthesis of hispidulene, the para-hydroxy benzaldehyde is treated with the acetophenone derivative. This acetophenone derivative and these two condense together to form the core structure, which can be further converted to hispidulene. So these are a couple of synthetic methods where Claisen Schmidt condensation is used as one of the crucial steps for the formation of natural products. In the summary, let us recap what we have studied so far. We have studied about the Beckmann rearrangement, the nomenclature of syn and anti-isomers, and the stereochemistry, how the stereochemistry is retained in the Beckmann rearrangement that we have seen. We have also studied about the mechanism and applications of Beckmann rearrangement. We have also studied about the Schmidt reaction, where how the reaction mechanism proceeds, and some of the applications of Schmidt reactions in the total synthesis we have seen. We have also did the comparison between Beckmann rearrangement and Schmidt reaction, because in the Beckmann rearrangement we will be starting from the oxime, whereas in the Schmidt reaction we will be directly starting from the carbonyl compound. And we also have studied about the Claisen Schmidt reactions, its mechanism and application. With that, we conclude this session, and we also conclude with this particular video the entire session on Organic Chemistry 3 paper in the Pharmaceutical Organic Chemistry paper 3. Thank you.